Okay, this visual was made by Matt and Joe, and we're looking at a golf ball that is hit off a tee, and the velocity is 26 meters per second at an angle of 35 degrees. And the question we came up with is we wanted to find out how far the ball traveled, assuming no air resistance, and we wanted to use this diagram to illustrate this principle. And so the first thing in terms of understanding this conceptually is looking at the golf ball as it is first hit. And so as it's hit at an angle, the ball is going to be going up. And these black arrows we wanted to use to represent the x and y velocities, um, because it's important to be able to break these down into the x and y components, to look at motion, because gravity is only acting in the y direction and not in the x. So the x-axis, these arrows going in the x direction, all of these have the same length, representing the velocity in the x that doesn't change. And then the y velocity is in the positive direction. And then as gravity slows it down, it brings it to a stop at the top. In the y direction at least, the x direction stays the same velocity. And then it starts to come back down. And then as it comes back down, the y velocity increases more and more. The x velocity stays the same. And that's the big conceptual ideas with that. So the first thing we need to do is break down the velocities in the x and y components. And so down here, we illustrated that with looking at the velocity in the x direction. And so we have the adjacent side, multiply cosine of 35 times 26 meters per second, and that'll give us 21.3 meters per second. And then for the y direction, we have to multiply by the sine of 35 because it's the opposite side of the right triangle, with the hypotenuse representing the full velocity. And so the x velocity won't stay, or will stay the same the whole time, the 21.3 meters per second. And this is going to be illustrated by the purple background. And then the y problem that we're looking at is going to have the black background. So what's really important with this question is we want to figure out how far it went. And so that variable is delta x, how far the ball went in the x direction. So that's our desired goal. So that variable is represented here as delta x. Now we know the x velocity right now, and that's 21.3, and that stays the same the whole time. We don't know delta x, and we don't know the time. So to find the time, that's where we're going to need the y problem. And this is where we take this y velocity, this is the initial y velocity, to figure out the time. And so we'll come up here, and this is looking at right here. This is the equation that we can use to figure out the velocity, or to figure out the amount of time that it takes to go halfway, because the final y velocity at the top is 0. And so we can take the initial y velocity, which is right here, 14.91, and place that in there. 0 for the y velocity at the top, plus negative 9.8 times t. So the time halfway is 1.52. And what I also wanted to illustrate too is you can see how these are symmetrical, just reversed. So this side is symmetrical to this side. And so it takes the same amount of time to get to the top as it goes to the full length. And so we multiply 1.52 seconds times 2. So the time for the full travel is 3.04. And we'll just illustrate the math here, multiplying the velocity times the time. And so the total distance traveled, at least when it hits the ground, is 64.8 meters. And so again, the big ideas with this is the fact that as this ball goes, the velocity in the y changes, comes to 0 at the top, and then increases more and more as it goes. And then it's equal and opposite velocity in the y at the end, and then the x velocity stays the same the whole time, assuming we're neglecting air resistance. And here's our references down here at the bottom. Thanks.